All right, everyone, we are back and we are on our Pset 2 solution video. So let's go ahead and get started. Let's go ahead and pull up Mathematica. I'm going to define some values here just so we can kind of work through this together. So I'm going to define right now a couple of things, quite a few things actually. So let's go ahead. I'm going to say my x bar, so let's see, nx equals 18, ny equals 37, nz equals 11, x bar x equals 120, x bar y equals 125, x bar z equals 110, sx equals 1, sy equals 0.5, sz equals 0.01. Great. And then I'm also going to read in my data here and here. So I'm going to call this my, actually, let's just do one. These are small enough. Even though I love looping, import. What do we got here? This is for problem 5. Let's do flatten. So we're going to say ps21 equals flatten here. And then we'll just do, oops. And then we'll do ps22. Right below it. Stop showing suggestions, please. ps22, ps22. There we go. Delete. We'll deal with you later. Fantastic. I'm going to get my t experimental value defined here. I'm going to give these. I'm going to pull these up here because I just want to be able to see. I want to grab this one too. I do have needs of testing. Student TCI, is it not? I'm just curious right now. Is there a separate? Or it could just be showing a blue and not appearing. There. Interesting. But irrelevant. So t experimental value. Okay, so we got our values all set up here. All right, let's see what we're being asked to do. Are x and y significantly different? We're not given the confidence percent, so we're going to do 95% confidence interval. Several different ways that we can kind of approach this. So first, I want my t experimental value, or tx. So I need x and y, so I need my x bar x, x bar y, sx, sy, nx, ny. So this is our t experimental value. We can also set up, and I'm just going to go down here, because I just want to, I want the quantile of, we can set up our new, you can actually set that up here. Yeah, there's a couple ways we can do this, and I want to kind of play around with some different ways. Simplest way would just be to do this. We can specify and we can kind of confirm. Let's see. Quantile second here. Make sure that we're here. So we can go ahead. Actually, yeah, that's what we can. I mean, this is just going to give us. So this is going to be a two-sided test. So we get the quantile of student distribution, and then new, and then we can actually, we need basically same thing here. Sx, sy, nx, ny, sx, sy. And then 95% divided by 2. That looks okay. So this would be our value. So this should be our basically theoretical value. Let's just double check and let's kind of confirm with our other approach, which is looking at our t-table. So if we look back over here, we found we want to see if they're different. So 025, whoops, get out of here. 025, our new is 21. 025, 21, 2.08, 2.078, pretty good. So does our t-experimental fall within plus or minus those bounds? Nope, that's going to be a what? A big old reject. So they are indeed different at that confidence interval. Does Z have a toughness smaller than Y at 1% significance level? All right, let's go. So now we're asking, is Z smaller than Y? Toughness smaller at that interval. So let's go ahead. Let's kind of use something similar here. So T experimental. So Z bar, or X bar Z, X bar Z, X bar Y, SZ, and Z. And I'm going to copy and paste this both into my new here. Does Z have a toughness smaller than Y? You see I'm really way over here, and then I'm going to copy this as well. Now remember, is this a left-tailed or right-tailed test? So it's left-tailed, so 1 minus 0.01. And that's it. We're not dividing by 2 here. 99%, so 0.01. That would be our quantile. Let's double check. So we have, if we want 99, basically 99%, so 0.01, and then basically, whoops, infinity, because we have 36. 36.01, so 2.3 something, 2.4 something. Kind of makes sense because we're closer to there. Looks nice. So are we, and remember, this is, if it's a less than, it's a negative, so we're still less than, so we are still in the reject region. Excellent. And we can kind of look at that here. So we're to the left. Remember, in that, actually, we can look at it right here. So our T experimental is falling. If we're looking at left-tailed test, it's the negative. So we're rejecting that H naught, that they're equal. Makes sense. So done here, done here. Does X come from population mean with a 90% confidence interval? So let's go ahead now and do something similar here. So I want my T experimental value. Mean, so I need my X bar X. My mu naught is 121. My SX NX. So that's my experimental value. Give me that number. I want the quantile as well, with a mean of 90% confidence interval, so 1 minus 0.1. And then divided by 2 because we're looking at less than that, all those good things. We are looking at, student distribution here because we're looking at the pure one, but now we're looking at nx because we're looking all at x minus 1. So that gives us our quantile here. Excellent. Again, let's double check one more time, and then we're going to trust it. So my nx is what? 18. So I'm looking at 0.0, or is it 0.1? Yeah, 0.1 divided by 2, so 0.05. What are we? 18, 17, 1.74. That's pretty nice. We're right on it. Excellent. I'm really enjoying this new approach. So this is going to be plus or minus. So again, once again, we're in a reject. So reject falls in there. Excellent. Does Y come from a population mean less than 121 at that 10% significance? Get out of here now. All right, get out of here. So let's go ahead and copy and paste this. Let's now go to here. So we're looking at y bar, or x bar y. 124 is our mu naught, sy, ny. Sy, ny. We're going to do ny minus 1. Let's see, significance, not divided by 2 this time, remember, because we're looking at mean less than, so it's left-tailed. So this is, if we go back to over here, in our left-tailed, we are definitely in a do not reject regime. That t experimental value is falling way over here, way to the right of that. Fantastic. And then finally, we can actually use our cool t-test functions now, because we can use our t.test to compare. So let's go to, we'll go to here. And actually we can do this less than, all this good stuff here, and actually get the p-value immediately. So let's go over here. What are we being asked? So t-test, we're going to use our data. So PS21, come from population of 298. We'll say alternative hypothesis. Basically unequal. We don't really even need to specify this here, but we can actually just show something like this. So that's our p-value, way greater than that 1% significance. So that is a do not reject. So excellent. Confidence level. Our PS2 and PS1 significantly different. If we want to compare the two, we can just say that, as we see here, we're going to say, are the means different? PS2 1, PS2 2, and then we got this. So this is a big old do not reject. Excellent. So we've got it. Basically saying, are the means, different? It's giving us something. It's asking if it's normally distributed, but we've got it. It's completely good. You could always double check if you would like. You can run the t experimental, and actually, why not? Just for fun. Let's go ahead and do. Actually, it's going to be a little bit annoying, but why not? Mean PS21, mean PS22. Oops. PS21, PS22, length, PS21, length, PS22. So t experimental is the same, which is nice. It's always a good check. And then we can also do, we're going to say that the new is going to be equal to this. And then we can paste that into our quantile, which is the 95%. Oops. And we can specify there. So that is a big old do not reject. Plus or minus those two bounds. Yeah, we're in the do not reject regime. That matches our p-value. Isn't life good? That's it. So we'll see you next time for Pset 3. Bye.